Okay, sorry, we had some issues with the connection. Now it should work again. Let us know in the chat if everything is working, but it seems so.
Io metterei dei pesi veri.
Sì, metto i pesi veri, metto tutte e due le misure e lancio.
Spettatori.
Okay, we just wait for the people to
reconnect,
and then we start again. Last 10 minutes.
I will set up anyway a Moodle or a Google Classroom to have a list of all students. There is a student who is asking whether this file will be uploaded on our website. No, it will stay on YouTube.
Yes, but you mean the video or the MATLAB file?
We can upload the MATLAB file.
Of course. MATLAB file, yes, we can upload it.
We can upload the MATLAB file, yes.
So you can play with it if you have, again, while people is connecting again.
Or a simpler, perhaps a simpler version
Maybe,
of it.
yes. Yeah, we have the same version of this without all the pictures and equations, so it's also faster to run. Again, while people is connecting again, I repeat, if you have questions, you can just write me. And I will be happy to answer to your questions, also if you have doubts. And maybe in this period you cannot come to the office, but you can call me on Skype if you have difficult questions or you need to ask more things. Okay, I believe we can go on.
Go on. Let us see what happens when we attribute realistic measurement errors or weights to range and range rate and solve for both together, using both observable together.
Okay, just to conclude the question that someone was asking before the connection went down, I use the switch function in MATLAB. It is like an if statement. It is just used to switch between cases. I switch on the variable, you can see here, just a moment that I go to the correct point of the code. Okay, here. For example, in this case, I have three cases possible. I wanted to switch on the variable observables based on the value that the variable observables assumes. If it is equal to range, you do this. If it is equal to rate, you do this one. If it is equal to both, you do this other statement. So it is just used to switch between cases. It is nothing related to orbit determination or estimation.
And the 1 and the 2 in H tilde refers to the row that you are selecting,
yes,
I guess.
Yes.
So if you are selecting range, only the first row and
all the columns.
All the columns.
In this case, you select only the second row and all the columns. Okay, you should know this.
Right, and
theory.
I didn't know it either way.
But I've done a MATLAB course, so
But
you are not
and
justified.
the other, you use everything.
Okay, in this case, I use the, let's call them correct weights for range and range rate. Okay, what does it mean, correct weights? These are the weights that have been used in generating the observables. Okay, so in a realistic case, these are the weights associated to the measurement system used. Okay, so I just control that I'm using the correct observable file because I have many. Yes, okay. So in this case, we are using different weights for range and range rate. I come back to that. As you can see in the weights definition here. Remember that the weights are equals to the inverse of the variance of the observations. Okay, so if you know the measurement system that you're using, they tell you it has a variance of I don't know, 1 centimeter. You can write 1 centimeter here. This is squared because this is the standard deviation. Okay, the standard deviation.
1 millimeter.
Yes, it was just a number, a random number. Yes, 1 millimeter in this case. Remember that the variance is the square of the standard deviation. Okay. In general, we talk about standard deviations because in Gaussian distributions they have a simple meaning. But in this case, here you have the standard deviation of the range is 1 millimeter, while the standard deviation of the range rate is 0.1 millimeters per second. Okay, so in this case I do exactly the same thing as before, so I run all the script and we see what happens. Okay, just a moment because it will be a bit slow. Yes, we will upload the script without all these equations, that will be much faster. There's an error. Okay, I see. Just a moment. Ok, now it should work.
Che cos'era?
Stava nella cartella sbagliata. Ok. Perché? Oh no, it switched to a wrong folder. I don't know why. Desktop.
Tieni conto che l'ho messo in didattica.
Sì, però non so perché non ce l'ha. Desktop.
Non è desktop.
Ah, ok.
È didattica.
Dentro documenti.
Ho Luciano.
Ah, ok. Non so dov'è.
Aspetta.
Vai. Vai.
File strumento. 2020.
Grazie. Okay, should work now. Sorry for the inconvenience. Okay, it's going. So now we are using the correct weight. So we are using together, first of all, we are using together both range and range rate. So we expect that augmenting the data number, we will have a faster convergence behavior, first of all. Secondly, since we are using the correct weights, so let's call them the true weights, what we will see is that we obtain the formal covariance matrix. Okay, so apart from saying that the estimated state is 3, for example, we can give also an uncertainty bound on that, because as you know, and as you will see again during the course, the basic assumptions in obtaining the least square solution is that the noise is white and the distribution of the noise is Gaussian. This implies that also the distribution of the solution is Gaussian. So you can use all the statistical properties of the Gaussian distribution also on the solution for x and v in this case. Okay, so I will explain you what does it mean. Okay, so let's see the residuals. We have run again with 4 iterations with the correct weights and so on. So we can see that, just a moment, here again.
Io manderei prima I grafici.
Okay.
Poi.
Okay, these are the graphs. These are always the same because they are prior to the first iteration. Then it reduces, and here we already see some noise, and then we will have, I believe, maybe another iteration is needed.
This is iteration 1 because
Yes.
we have 2 now.
Yes, and here you can see we have reached convergence again. Okay, these are the range residuals. We have reached convergence on range, while on range rate maybe we need another iteration. As you can see here, we have still a bit of noise. On range, as we have said, we have perfect convergence. Okay, and we will see it. We see it from the mean that is really close to 0. The RMS of the residuals, that, remember, should be equal to the standard deviation of the noise of the data point. I recall you that the noise on the range was 1 times 10 to the minus 3, so this is almost the same number. And the sum of squares is 600. That is exactly the number of observations that we had, because we had 1 observation per second for 100 seconds. Okay. And I believe that we have almost converged also on range rate. Yes, you can see it from here. We have the mean that is very small, the RMS that is quite similar to 1 to the power of minus 4, that it is the true noise on the range rate, and the SOS, the sum of square, is really near to 600. Probably another iteration on range rate would be useful.
Perhaps.
Perhaps.
I think statistically they are identical.
Yes.
There is only one interesting remark here. You saw that while range residuals looked white, range rate did not yet. And this is a consequence of the fact that probably for this particular problem, range rate were very accurate, more accurate, and so they could still feel some mismatch between observed and computed.
Yes.
While for range, range was were so noisy that one couldn't see any particular signature.
In this case here you have it. At the second iteration, the range looks already converged, while the range rate not. And in this case, using range rate is useful, because if you looked only at range, you would have said, okay, I've converged, the values that I get here are correct, more or less.
But you see that, for example, the number of square, the sum of square, is not really 600. So
It's
this points to the fact that you are not really there, you are not really at convergence.
Yes, that's it. In this case, we have no more time, but in a later lesson, if we have time, we will see how to quantify the sensitivity of the measurements to certain parameters. Okay.
So either on Wednesday or Thursday, we will do a more complex problem with a Keplerian motion of a satellite around the planet. Now, so this class ends here. I would like to have some feedback about the effectiveness of the material that we have presented and the way in which these telematic lectures work. You need not, if you want to write to me on the chat right now, or please send me an email later if you wish. I will wait a couple of minutes to see some feedback from the chat.